At the end of section 2.1, we started to see the idea of what we were calling a limit. And here in section 2.2, we are going to formally define the limit of a function and then start looking at all the properties and laws of limits. The idea that we saw in the last section was of one thing approaching a certain number as something else, usually x, got very close to another number. So as our definition, we will say that f of x is defined when x is near the number a. Thus, f of x is defined on some open interval that contains a, which really just means if you think of the horizontal axis, you'd have at some point a somewhere, and this is saying that f of x is defined on an interval of numbers around that value of a. But we don't have to have the function defined at a itself. That isn't necessary. So in this instance, we can then say the limit as x approaches a of f of x is equal to L. We're allowed to say that with that notation and also with the wording that I just said, the limit of f of x as x approaches a is L. We're allowed to say that if the values of f of x approach L as x approaches a from either side. So you can think as x is getting closer to a from either the left or from the right, then the limit essentially exists if our function is approaching this value L. And again, we don't need f of x to be defined when x is equal to a. So let's start by looking at an example. Let's guess the value of the limit, if it exists, by evaluating the function at the given numbers. So here we are trying to guess the value of the limit as x approaches 3 of the function x squared minus 3x divided by x squared minus 9. So I have it typed out, but written out we actually see the fraction a little bit more explicitly. So we're going to see if this limit might exist by evaluating this function, meaning the fraction that I have there, at the values 3.1, 3.01, 2.9, and 2.99. And you can think that these numbers are essentially very close to the value of 3, which is what we are interested in. So we can evaluate at those numbers, and we're going to do a couple, but then we're actually going to draw the graph to remind ourselves of something from pre-calculus, and then maybe we can see what is going to happen. So let's start by just plugging in a couple of numbers. And I'm going to do the ones that are pretty close to 3. So I'm going to look at x equal 2.99, and we're going to see what happens. So this just means I need to take 2.99, square it, and then subtract 3 times 2.99, and then divide by 2.99 squared minus 9. And then let's also do the same thing for when x is equal to 3.01. And there I would just have 3.01 squared minus 3 times 3.01, and then divide that by 3.01 squared minus 9. So I'm going to grab my calculator and calculate these. So what we get for those values is when x is equal to 2.99, we get the function is equal to 0.499, where I've rounded to 3 decimal places. And then when x is equal to 3.01, the function is equal to 0.501. Keep in mind these values now that we've reached here, they both look awfully close to the number 0.5. If you were to round them to 1 decimal place, they would in fact be the same value. So to get a little bit of an understanding now of maybe we might be able to suspect what this limit is equal to, like we might say maybe this is equal to 0.5. Let's do what I suggest in this bullet point. Let's draw the graph and then see what is going on. So first of all, this is a rational function. X squared minus 3x divided by x squared minus 9. The domain of this function doesn't allow x to be positive or negative 3, because that would make the denominator equal to 0. But instead of this turning into an asymptote at both of those, one of those points actually becomes a hole in the graph. And the reason why is because we can actually simplify this expression by factoring. And then we can cancel out where there was a hole, which is at x equal 3, and we find that our function is actually just x divided by x plus 3, which gives us a vertical asymptote of negative 3. The vertical asymptote is at negative 3, and then we can also recognize from our knowledge of pre-calculus that there will be a horizontal asymptote at y equal 1. We're actually going to figure out with limits how that horizontal asymptote is what it is later on in a different video. But for now, we can just do a little sketch. So I've got my coordinate axis. I've got that at positive 3 there's going to be a hole, but at negative 3 there's a vertical asymptote. And then at y equal positive 1 there is a horizontal asymptote. And then we could also think to ourselves maybe where some intercepts are. If you let x equal 0, you would get y is equal to 0. So we actually have an x and a y intercept at the same place. And then finally, we can remember that rational functions have a shape that is essentially a curve that approaches the asymptotes in usually two different quadrants. But as I continue my graph to the right, the moment I cross x equal to 3, there's actually going to be a hole in a part of this graph. So I'm going to just draw that like this. Again, this is just a sketch, and then I approach the asymptote. So now when it comes to the question of what is this limit equal to, think that as x is approaching 3 from either side, either the left or the right, meaning like x equal 2.99 and x equal 3.01, the value of our function is approaching the same point where this hole is. Notice that our function is not defined at x equal 3, but the values of our graph, they're both approaching the same place. And where is that? It's somewhere between 0 and 1. So based off of my crude sketch here, it's some fraction, some number between 0 and 1. And that number is just 0.5, which we figured out numerically. So again, remember that this function is not defined at, I should say here, x equal 3. It's not defined at x equal negative 3 either, but what was important is that when we evaluated our limit as x approaches 3, our function didn't have to be defined there to actually figure out this limit. Okay, let's look at another example. Guess the value of the limit as x approaches 0 of sine x divided by x. So first of all, keep in mind, if you were to plug in 0 to the function, you would get sine of 0, which is 0, divided by 0, which is undefined. So this function is not defined at x equals 0. But if we plug in some values, we might be able to get to some conclusion about this. So plug in some values for x, but keep in mind with your calculator, you want to be using radian mode. This is actually important pretty much any time that you're going to be using trigonometric functions in a calculus class. More often than not, you're going to be using radian mode. So take a few minutes and see what you get by just plugging in numbers that are close to 0. I would suggest numbers like 0.1, 0.01. Those are positive numbers, but then also come from the left, negative 0.1, negative 0.01 and see what you get. So here's a table of values that I get. When I use x equals 0.1, the value of the function is 0.998. When I use x equals 0.01, the value of the function is 0.99998. And I actually get those same values when I use the negative versions of those x values. So if I was to guess what the limit is, it seems that as x is getting closer to 0, right, which would be sitting right here between 0.01 and negative 0.01, it looks like the function value would be what seems to be close to those numbers. If you were to just do some rounding, it looks like that's approaching 1. So it seems like this function is actually approaching 1. And if you were to actually go and graph this function, you would get some confirmation about that. Next example, let's guess the value of the limit as x approaches 0 of the function sine, but this time of pi divided by x. Here the fraction is inside of the sine function. Here's one way to approach this. What happens to the fraction pi over x as x gets closer to 0? If you were to just think pi divided by x as x approaches 0, you're taking a number that's constant, pi, and you're dividing it by smaller and smaller numbers, which is the same thing as dividing by fractions. Whenever you divide by a fraction, you reciprocate, which then turns into taking pi and actually multiplying pi by larger and larger numbers. What this means is that pi over x as x approaches 0 approaches infinity. And you can try this out for yourself. Take pi and divide it by a really small number like 0.00001 and see what you get. Do you get something that's bigger than pi? That'll help you understand why this is approaching infinity. So that means that as x is approaching 0, the inside of this sine function approaches infinity. So now the question is what happens as the input of the sine function goes to infinity? What happens to the sine function? As we saw, the sine function is just a wave that keeps oscillating over and over. But it never stops, whether you're going to positive infinity or whether you're going to negative infinity. But it's always between 1 and negative 1, which means it'll never stop and land on a certain number. So what this actually means is that there is no limit to this function, sine of pi over x, as x approaches 0. It's always going to be going between 1 and negative 1. What that means is if it doesn't actually settle on a number, then there's no limit. The limit does not exist. So now we have a couple ideas how to see if a limit does exist by some numerical guessing or by graphing, or how to see when a limit does not exist if we actually don't reach a certain number. So with these ideas, we can break down the definition of a limit to what are called one-sided limits. So first, we write the limit as x approaches a with a little negative at the top as a superscript of the function f of x equal a. And what this is really saying is the left-hand limit of f of x as x approaches a, or the limit of f of x as x approaches a from the left. This limit is equal to capital L, some actual number, if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a with, and this is important, x less than a. So we're taking values of x that are below the value of a. There is also a similar definition for a right-hand limit, just essentially using a superscript of a plus. And really what this comes down to is just recognizing the notation and how that relates to a left-hand or a right-hand limit. So then furthermore, the limit of f of x as x approaches a equals L, meaning this is true if and only if then these other things are true. The left-hand limit equals L and the right-hand limit equals L. So what this means is if we find the left and the right-hand limits and they both equal the same value, L, that now means that the limit of the function f of x as x approaches a exists, and what it equals is this letter L, which again is going to be a constant whenever we find that the limit exists. So now here's an example from the book, number 7 on page 92. And this is just going to be some practice of finding some left or right-handed limits, and then also some limits just overall. So for the function g, whose graph is given, state the value of each quantity if it exists. If it does not exist, explain why. So we'll start with part A, the limit of our function g of t as t approaches 0 from the left. If we look at the horizontal axis for t, and we find out where t is equal to 0, if we're approaching from the left, that's what we're considering in part A, what we would actually be doing is following the graph as the input is approaching 0. And our graph is approaching the value of -1. That's where this dot is right there. So our function is approaching -1 as t is approaching 0 from the left. What this means is, for part A, the limit as t approaches 0 from the left of g of t is equal to -1. But now consider part B, the limit of g of t as t approaches 0 from the right. If I was to consider that, now I'm using another part of the graph that's on the right-hand side of t equal 0. And we can see that if I follow that graph, it's not approaching the same place that we had before. It's approaching -2. So then part C says, what is the limit of g of t as t approaches 0? Which essentially is saying, now that you've figured out the left and the right-hand limits, are they equal? No. So this limit does not exist. And the reason why is because the right and the left-hand limits are not equal. Okay, let's look at part D. The limit of g of t as t approaches, and this is 2 from the left. So as t is approaching 2 from the left, we're looking at the graph that is to the left of t equal 2. We can see that it's approaching this value of 2 up there. But if I was to look at approaching 2 from the right, which is what part E says, then I'm using a different part of the graph. That's approaching 0. And then in part F, what is the limit of g of t as t approaches 2? Again, the right and the left-hand limits are not equal to each other, so this also does not exist. Also, we can point out, related to this value of t equal 2, in part G of this problem, it asks, what is the function value when t is actually equal to 2. Notice that's not even the same thing as the left and the right-hand limit. It's just 1. Again, reiterating that we can still find limits even if the value of the function is different at that point. And then finally, part H, just to see how this relates to when a limit does exist. The limit of g of t as t approaches 4. T approaching 4 means that our function is approaching from the left and the right, and we can see that that is just right there. It's already on the graph, and the graph meets at that point, and that value is just 3. This is somewhat similar to the example that we did earlier, where the function was meeting at a certain point, even though the function didn't exist there. So it is similar in that respect. So then finally, infinite limits. So for example, find the limit as x approaches 0 of the function 1 over x squared. So again, notationally, we can write that like so, by calculating some values. So the question is, as we get closer and closer to 0 on either side, we want to see what the function is getting close to. And this is very similar to something that we saw before with pi over x. As x gets smaller, as in approaching 0, this fraction actually turns into a very large number. And that doesn't matter if it's positive or negative, and this is because we are squaring the function values. So again, let's just try this out. We'll take numbers like 0.1, 0.01. You can do other ones. And let's just see what we get when we plug in those values. Again, you are essentially just taking the number 1 and dividing by the square of these numbers. So for example, 1 divided by 0.1 squared, that would just give me 100. But if it was negative 0.1, I would still get the same output, because we're squaring. A negative squared turns into a positive. And then if you do the same thing with 0.01, squaring that in the denominator, you end up with 10,000. So our suspicion is correct, where we're saying if we keep dividing by smaller and smaller numbers, we actually get larger and larger results. And it doesn't matter if they're negative or positive when we're putting them in. This goes back to looking again at a rational function graph. But the value of our function is always positive, and essentially what we have is a vertical asymptote at x equals 0. So now we're learning a little bit more about these things that we saw in pre-calculus. As x is approaching 0 from the left or from the right, our function is getting larger and larger. It's going up as it's approaching that vertical asymptote. And that happens on either side of x equals 0. So in this sense, we would say that the limit as x approaches 0 of 1 over x squared is infinity. But infinity is not a real number, because we can't actually define what infinity is. So we would say that the limit does not exist. Because if you were to say that the limit does exist, it means that you can find the endpoint of infinity, which isn't possible. So we don't regard infinity as a real number, and we don't say that the limit exists, but this still does give us an idea about the function. So it is important to say that the limit is equal to infinity, but it's also important to recognize that that means the limit does not exist. So then we formally define that on the next page. Let f be a function defined on both sides of a, except possibly at a itself. Then the limit as x approaches a of f of x equals infinity means that the values of f of x can be made arbitrarily large by taking x sufficiently close to a, but not equal to a. We can also use similar notation if the value of the function becomes large in the negative direction, using negative infinity instead of positive infinity. And this relates to vertical asymptotes for rational functions. Finding that the function approaches positive or negative infinity as x approaches either side of a value a means that there is a vertical asymptote at x equal a. So then finally, let's look at one example related to these infinite limits. Determine the infinite limit of the function x plus 1 divided by x minus 5 as x is approaching 5 from the left. And really the main question here is, it's going to be an infinite limit because that was said to us in the example, but is it positive infinity or negative infinity? So first of all, we know that there's a vertical asymptote at x equal 5. So we know that this function is going to be getting either large in a positive or a negative direction. What will help us determine that is by considering what hand limit we are looking at. In this case, we're approaching 5 from the left. So as x approaches 5 from the left, the numbers are smaller than 5. So if you take numbers that are smaller than 5, but then you subtract 5 from those numbers, you're taking a number that's smaller than 5, subtracting 5 from it, you're going to end up with negative numbers. So x minus 5 is negative. You can reason this with yourself by just saying 4 is less than 5, but 4 minus 5 is negative 1. So if you're choosing numbers from the left of 5, you're going to get a negative value for anything x minus 5. So what this means is that our infinite limit is going to be negative because what I'll have is a number plus 1 in the numerator, which is positive, divided by a number minus 5, which will be negative if we're using numbers that are very close to 5 on the left. So we get negative infinity. The limit doesn't exist, but that does give us an idea about this function. That's it for this section. In the next section, we're going to take a look at some limit laws.